Today I'll be presenting a paper that I personally find extremely cool. It digs into the vision transformers and reveals hidden structures inside the attention that no one really understood before. And based on this discovery, it builds a much more accurate and efficient attention approximation. The whole paper is like uncovering the secret geometry inside of it. So vision transformers are everywhere. Do you know clip vid models? But they are expensive. Self-attention scales quadratically with the number of patches. Over the years, we had tons of approximations like Nystrom, performers, linear transformer, etc. And these methods often work surprisingly well. But here's a problem, we actually don't know why they work. We didn't have a theoretical or structural explanation. This paper finally provides one. It says the attention inside the VITs is secretly structured, extremely structured, and we can exploit that. VIT splits an image into n patches, as we can see in the figure, and each layer applies a full self-attention, so it's n-squared interactions, quadratically large. High resolution image means like 196 or 576 tokens, so it blows up. We need approximation. But current approximations were built on heuristics. This set up the motivation of this paper. If attention is truly structured, not random, then we can approximate it in principle, theory-backed way. All current models, Nystrom, sparse patterned, and kernel tricks choose approximations based on an assumption. Low rank, sparsity, locality, and smoothness. But none prove that attention actually has a properties in real vids. This paper flips the theory. Instead of designing approximation first, it looks inside the vids and discovers concrete structural patterns, and then design an approximation based on those patterns. The paper has four main contributions. First of all, it discovers massive tokens. Tokens with huge key value norms that attract most attention. These are the true attention sink. Also, it discovered artifact tokens, the fake sink that appear only when massive tokens are removed. It gives a spectral explanation. The token corresponds to dominant eigen directions of attention. So based on this, they propose fast Nystrom attention, a principled, stable, efficient approximation. Here's the key idea behind the math. I won't show equation on all the equation on the slides, but let me explain the mechanism in the words. Attention computes similarly between queries and keys. If a key vector have a much larger magnitude than the others, its dot product with every query will be large, so this part will be large. Since softmax amplifies large values, this token will be attracting a huge amount of attention, even if its content is meaningless. This means attention has built-in tendency to form dominant directions wherever the key norms are uneven. This is the foundation behind massive tokens. When you inspect Wit's attention maps across layers and heads. You see bright lines. Certain patches attract attention almost regardless of the input image. These are the massive tokens. They appear because their key vectors have unusual large norms. The transformer uses them as anchors that stabilize the distribution. Crucially, these massive tokens are extremely consistent across image, across layers, across training paradigms. They absorb attention like black holes. Let me go deeper and describe what's happening mathematically. Although I'm not showing the equation conceptually, the attention logits are computed from Q times K transpose. If the key vector has a huge magnitude, it essentially becomes dominant in the linear operator QK transpose, which is just what I just mentioned. So, this is why they dominate every attention map. This is not accidental, this is spectral property of the attention mechanism. So, there's so if you remove the massive token, this is where the story gets interesting. By for example, if we mask the massive tokens, the transformer automatically promotes other token to become the next biggest attractors. These are called artifact tokens. They are not meaningful. They are not stable. They are just next biggest directions once you remove the dominant ones. This is exactly what happened when you remove the top eigenvectors of the matrix. The next eigenvectors become dominant. This proves that massive tokens are not surface level quirk. They reflect true underlying spectral structure. So now we have a big picture. Attention in bits is heavily dominated by a small number of tokens. Everything else is low rank residue. This explains why approximation works. We only really need to capture a handful of principal directions. The paper then used the insight to design and improve Nystrom method. So let me explain the algorithm with the screenshot you see. We run the width up to an intermediate layer where massive tokens started to emerge. Then we iteratively mask the current sync tokens, and then we recompute attention at the later detection layer. So we detect new tokens whose attention from CLS exceeds self-attention. These are the new syncs. This iterative process uncover both massive token and artifact token, and the final set of the massive token become our landmarks. The artifact tokens become masked because they introduce noise. In the old Nystrom, we call vanilla Nystrom, the approximation works only if the chosen landmarks captures the dominant directions of the attention matrix. Random landmarks fail because they miss the actual spectral direction. In massive tokens, however, are the top directions. They correspond to the largest singular values of QK transpose. So, choosing massive tokens as landmarks gives a mathematically aligned low rank basics. And masking artifact tokens prevents softmax from applying fake eigendirection. We take massive tokens as as landmarks. Sorry. And we take artifact tokens as in the softmax. We compute three components: token to landmark, landmark to landmark, and landmark to token attention. Then we reconstruct the full attention using a Nystrom style procedure. This is actually presented in the vanilla Nystrom system, but we refine this part only, and we can enhance the whole part. Because the landmark matrix captures the real dominant eigenspace, the reconstruction is far more accurate and far more stable. So let me give a strongest conceptual explanation without formulas. The attention operator is a matrix whose structure is governed by the magnitudes of key vectors. Massive tokens correspond to dimensions in which the operator has extremely high spectral energy. These are the direction you must preserve in any low rank approximation. And any token with large KV norms become part of the dominant subspace. Therefore, attention is inherently low rank because VIT generates a heavy-tailed distribution of key norms. FNA succeeds simply because it approximates the true top eigenstructure. Nystrom fails because it samples directions that don't matter. Here are the numbers. Send computational budget, completely different accuracy across Dino V2, clip, and supervised fit. FNA recovers far more accuracy than vanilla Nystrom. Linear probes actually improves by 10 to 20%, and zero shot clip improves drastically. FNA is not slower, it's just smarter. It uses structure Nystrom ignores. So here are some ablation. Ablation tells the real story that if you remove the artifact masking, perform drops. If you choose random landmarks, perform collapse to Nystrom level. If you select top norms token instead of full algorithm, it's almost as good, but proving that norms are the real root cause. And masking in the wrong place also hurts. So this proves massive token and artifact tokens are real phenomena, not trending quirks. The main limitation includes sync detection algorithm is expensive if you run it fully, and different training paradigm produce slightly different sync distribution, and the theory is empirical. It does not yet have a full formal theorem. And FNA still cannot perfectly match full attention. So the future direction is applying sync-based structures to LLM and hardware co-design using sync-aware attention, combining syncs with sparse attention, understanding how to deliberately control the regularize massive tokens during training. So this paper opens a lot of doors. To wrap up, this paper reveals that VIT attention is not random. It is a deep spectral structure controlled by massive token. Artifact tokens appear when you disturb the structures. Based on the insight, the author built an efficient and accurate approximation called fast Nystrom attention. It has both theoretical motivation and strong empirical performance. It is a great example of theory and engineering meeting the right place. So, this is my presentation this week. Thank you so much.